The equipment grounding conductor, or EG, is designed to provide a low impedance path for fault currents to return to the electrical source. The primary purpose of the EGC is to protect individuals from electric shock by preventing the equipment enclosure or frame from reaching a hazardous voltage potential during a fault condition. According to the National Electrical Code, NEC, the EGC size must be based on the overcurrent protection device OCT protecting the circuit. The minimum size requirement for an EGC is typically number 14 American wire gauge, AUG, copper, or number 12 AWG aluminum. The EGC does not need to be the same size as the current carrying conductors for several reasons. Firstly, the EGC only needs to carry fault currents, which are typically much lower than the rated current of the circuit. Secondly, oversizing the EGC does not provide any additional protection against electric shock or ground faults. Thirdly, using a larger EGC than necessary can increase material costs and make the installation more difficult to work with. For instance, if a circuit is protected by a 15-amp circuit breaker, the EGC size should be determined according to NEC Table 250.122. For a 15-amp circuit, the minimum EGC size is number 14 AWG copper or number 12 AWG aluminum. Using a number 10 AWG EGC, which is the same size as the current carrying conductors in this example, would not provide any additional benefit or protection. In conclusion, while a larger EGC may not be detrimental to the system's operation, it is unnecessary and can be uneconomical. The EGC should be appropriately sized according to the NEC requirements to ensure adequate protection against electric shock and ground faults. Understanding the purpose and sizing requirements of the EGC is crucial for ensuring electrical safety and compliance with industry standards. The NEC provides specific guidelines to determine the correct EGC size based on the overcurrent protection device protecting the circuit. These guidelines are designed to ensure that the EGC can safely carry fault currents back to the source, tripping the overcurrent protection device and clearing the fault. It's important to remember that the EGC primary function is to provide a low impedance path for fault currents, not to carry the normal load current of the circuit. Therefore, it doesn't need to be sized the same as the current carrying conductors. Using a larger EGC than required doesn't offer any additional safety benefits and can increase costs and installation complexity. Instead, focus on adhering to the NEC guidelines and selecting the appropriate EGC size based on the overcurrent protection device. This will ensure adequate protection against electric shock and ground faults while maintaining cost-effectiveness and ease of installation. Now let's delve a little deeper into the specifics of EGC sizing and the relevant NEC sections. The NEC provides tables and guidelines for determining the minimum size of the EGC based on the rating of the overcurrent protection device. These tables, such as Table 250.122, specify the minimum EGC size for various overcurrent protection device ratings. To use these tables, you need to know the ampacity of the overcurrent protection device protecting the circuit. Once you have this information, you can look up the corresponding minimum EGC size in the table. It's important to note that the NEC specifies minimum sizes for EGC. You are always permitted to use a larger EGC than required, but it's generally not necessary and can be wasteful. The NEC also provides specific rules for EGC in different types of wiring methods, such as rigid metal conduit, electrical metallic tubing, and flexible metal conduit. These rules may require the EGC to be installed inside the conduit or raceway along with the circuit conductors. The NEC also addresses the use of metal enclosures as EGC. In some cases, the metal enclosure of a piece of equipment or a raceway can serve as the EGC, provided that it meets certain requirements. These requirements typically involve ensuring that the metal enclosure is properly bonded and has sufficient conductivity to safely carry fault currents. Another important aspect of EGC is bonding. Bonding refers to the process of connecting all metal parts of an electrical system together to create a common ground potential. This helps to prevent voltage differences between different metal parts, which can create a shock hazard. The NEC has specific requirements for bonding, including the use of bonding jumpers and bonding bushings. These requirements are designed to ensure that all metal parts of the electrical system are effectively bonded together. It is important to ensure that all EGC connections are properly made and tightened. Loose or corroded connections can increase the impedance of the EGC path, reducing its effectiveness in carrying fault currents. Regular inspection and maintenance of EGC connections are essential for maintaining electrical safety. In addition to the NEC requirements, it's also important to follow any local codes or regulations that may apply to electrical installations in specific areas. Local codes may have additional requirements for EGC or other aspects of electrical safety. It is essential to be aware of and comply with all applicable codes and regulations. Let's consider some additional examples to illustrate the principles of EGC sizing. Suppose you have a circuit protected by a 30 amp circuit breaker. According to NEC Table 250.122, the minimum EGC size for a 30 amp circuit is number 10 AWG copper or number 8 AWG aluminum. If you were to use a number 8 AWG copper conductor for the circuit conductors, you would still only need a number 10 AWG copper EGC. Using a number 8 AWG copper EGC would not provide any additional benefit. Now let's say you have a larger circuit protected by a 100 amp circuit breaker. In this case, NEC Table 250.122 specifies a minimum EGC size of number 8 AWG copper or number 6 AWG aluminum. If you were using number 3 AWG copper conductors for the circuit conductors, you would still only need a number 8 AWG copper EGC. The EGC size is determined by the overcurrent protection device rating, not the size of the circuit conductors. One common misconception is that the EGC needs to be sized to handle the full load current of the circuit. However, as mentioned earlier, the EGC only needs to carry fault currents, which are typically much lower than the rated current of the circuit. The overcurrent protection device is designed to trip and interrupt the circuit if a fault occurs, limiting the amount of current that flows through the EGC. Another important consideration is the type of equipment being served by the circuit. Some types of equipment, such as motors, may have higher fault current potential than others. In these cases, it may be necessary to increase the size of the EGC to ensure that it can safely carry the fault current. The NEC provides specific guidance on sizing EGC for different types of equipment. When selecting an EGC, it's also important to consider the environmental conditions in which it will be installed. In corrosive environments, it may be necessary to use a corrosion-resistant EGC material, such as copper or stainless steel. The NEC provides guidelines on selecting appropriate EGC materials for different environmental conditions. Proper installation of EGC is also crucial for ensuring their effectiveness. EGC should be installed in a manner that minimizes impedance and provides a reliable path for fault currents. This may involve using short, direct runs and avoiding sharp bends. All EGC connections should be properly made and tightened to ensure a low impedance connection. In summary, the EGC is an essential component of an electrical system, providing a low impedance path for fault currents and protecting individuals from electric shock. The EGC should be sized according to the NEC requirements based on the overcurrent protection device protecting the circuit. It's important to understand that the EGC does not need to be the same size as the current carrying conductors, as it only needs to carry fault currents. By following the NEC guidelines and best practices, you can ensure that your electrical systems are safe and reliable. Now, let's expand on some of the specific scenarios where understanding EGC sizing is particularly critical. Consider a situation involving a long circuit run. In long circuit runs, the impedance of the conductors can increase, which can affect the performance of the EGC. The NEC addresses this issue by requiring that the EGC be sized to compensate for the increased impedance of long circuit runs. This may involve increasing the size of the EGC or using a parallel EGC. Another scenario to consider is when dealing with multiple circuits in a single raceway. When multiple circuits share a single raceway, the NEC requires that a single EGC be sized to serve all of the circuits. The size of the EGC must be based on the largest overcurrent protection device protecting any of the circuits in the raceway. This ensures that the EGC is capable of carrying the fault current from any of the circuits. In industrial settings, where there may be large motors or other heavy equipment, EGC sizing is particularly important. Large motors can generate high fault currents, which can quickly damage equipment or cause injury if the EGC is not properly sized. The NEC provides specific guidance on sizing EGC for motors, taking into account the motor's horsepower and voltage rating. Another area where EGC sizing is critical is in healthcare facilities. Healthcare facilities have stringent requirements for electrical safety due to the presence of sensitive medical equipment and the potential for patients to be particularly vulnerable to electric shock. The NEC has specific requirements for EGC in healthcare facilities, including requirements for redundant grounding and bonding. When working with older electrical systems, it's important to be aware that the EGC sizing requirements may have changed over time. Older systems may not have EGC that meet current code requirements. In these cases, it may be necessary to upgrade the EGC system to ensure compliance with current safety standards. When making modifications or additions to existing electrical systems, it's important to ensure that the EGC system is properly extended and sized to accommodate the new loads. This may involve adding new EGC conductors or upgrading existing EGC conductors. It's also important to ensure that the new EGC conductors are properly connected to the existing EGC system. In addition to the NEC requirements, it's also important to consider the manufacturer's recommendations for EGC sizing. Some equipment manufacturers may specify a minimum EGC size that is larger than what is required by the NEC. In these cases, it's important to follow the manufacturer's recommendations to ensure proper equipment operation and safety. When in doubt about the proper EGC size, it's always best to consult with a qualified electrical engineer or electrician. They can assess the specific application and provide guidance on selecting the appropriate EGC size and installation methods. Remember, electrical safety is paramount, and proper EGC sizing is a critical component of ensuring electrical safety. By understanding the principles of EGC sizing and following the NEC guidelines, you can help to protect people and property from the hazards of electric shock and ground faults. Now let's discuss the materials commonly used for equipment grounding conductors. Copper is a popular choice for EGC due to its excellent conductivity, corrosion resistance, and ease of installation. Copper EGC are typically used in residential, commercial, and industrial applications. Aluminum is another option for EGC, particularly in larger sizes. Aluminum is lighter and less expensive than copper, but it has lower conductivity. When using aluminum EGC, it's important to ensure that they are properly terminated to prevent corrosion. Steel is sometimes used for EGC, particularly in the form of rigid metal conduit or electrical metallic tubing. Steel EGC are strong and durable, but they have lower conductivity than copper or aluminum. When using steel EGC, it's important to ensure that they are properly bonded to provide a low impedance path for fault currents. In some cases, the metal enclosure of equipment can be used as an EGC. However, the enclosure must meet certain requirements to ensure that it can safely carry fault currents. These requirements typically involve ensuring that the enclosure is properly bonded and has sufficient conductivity. When selecting an EGC material, it's important to consider the environmental conditions in which it will be installed. In corrosive environments, it may be necessary to use a corrosion-resistant EGC material such as copper or stainless steel. The NEC provides guidelines on selecting appropriate EGC materials for different environmental conditions. Proper installation of EGC is also crucial for ensuring their effectiveness. EGC should be installed in a manner that minimizes impedance and provides a reliable path for fault currents. This may involve using short, direct runs and avoiding sharp bends. All EGC connections should be properly made and tightened to ensure a low impedance connection. It's also important to protect EGC from physical damage. EGC should be installed in a way that prevents them from being crushed, cut, or otherwise damaged. This may involve using conduit or other protective measures. Regular inspection and maintenance of EGC are essential for maintaining electrical safety. EGC should be inspected periodically to ensure that they are in good condition and that all connections are tight. Any damaged or corroded EGC should be replaced promptly. In addition to the NEC requirements, it's also important to follow any local codes or regulations that may apply to electrical installations in specific areas. Local codes may have additional requirements for EGC or other aspects of electrical safety. It is essential to be aware of and comply with all applicable codes and regulations. By using the appropriate EGC materials, installing EGC properly, and maintaining them regularly, you can ensure that your electrical systems are safe and reliable. Remember, electrical safety is paramount, and proper EGC installation and maintenance are critical components ensuring electrical safety. Now let's address some frequently asked questions about equipment grounding conductors. Firstly, is it acceptable to use the neutral conductor as an equipment grounding conductor? The answer is generally no. The NEC prohibits the use of the neutral conductor as an EGC in most situations. The neutral conductor is intended to carry normal load current, while the EGC is intended to carry fault current. Combining these two functions in a single conductor can create a shock hazard. Secondly, what is the difference between grounding and bonding? Grounding refers to connecting an electrical system to the earth, while bonding refers to connecting all metal parts of an electrical system together to create a common ground potential. Grounding helps to stabilize the voltage of the electrical system, while bonding helps to prevent voltage differences between different metal parts. Thirdly, how do I test an EGC to ensure that it is working properly? There are several ways to test an EGC. One common method is to use a low resistance ohmmeter to measure the resistance between the equipment enclosure and the grounding electrode. A low resistance reading indicates that the EGC is providing a good path for fault current. Another method is to use a ground fault circuit interrupter GFCI tester to verify that the GFCI trips when a ground fault is simulated. Fourthly, can I splice an EGC? Yes, EGC can be spliced, but the splices must be made in a way that ensures a reliable electrical connection. The NEC specifies the types of connectors and methods that are permitted for splicing EGC. Fifthly, what size EGC is required for a subpanel? The EGC for a subpanel must be sized according to NEC Table 250.122, based on the overcurrent protection device protecting the feeder to the subpanel. The EGC must also be installed in a manner that provides a low impedance path for fault current. Sixthly, is it necessary to run an EGC to a detached building? Yes, the NEC requires that a separate EGC be run to a detached building if the building is served by a multi-wire branch circuit or if it contains equipment that requires grounding. The EGC must be sized according to NEC Table 250.122, based on the overcurrent protection device protecting the feeder to the detached building. Seventhly, what are the requirements for EGC in hazardous locations? Hazardous locations have specific requirements for EGC due to the increased risk of explosion or fire. The NEC provides detailed guidance on grounding and bonding in hazardous locations. Eighthly, can I use flexible metal conduit as an EGC? Flexible metal conduit can be used as an EGC under certain conditions, but it must meet specific requirements. The NEC specifies the types of flexible metal conduit that are permitted to be used as EGC and the conditions under which they can be used. Ninthly, what are the requirements for EGC in swimming pools? Swimming pools have stringent requirements for EGC due to the increased risk of electric shock. The NEC provides detailed guidance on grounding and bonding in swimming pools. Tenthly, how often should I inspect my EGC system? It is recommended to inspect your EGC system periodically, at least once a year, to ensure that it is in good condition and that all connections are tight. Any damaged or corroded EGC should be replaced promptly. By understanding these frequently asked questions and their answers, you can gain a better understanding of EGC and their importance in electrical safety. Remember, if you have any questions or concerns about your EGC system, it's always best to consult with a qualified electrical engineer or electrician. Finally, let's consider the future trends in equipment grounding and electrical safety. As technology advances and electrical systems become more complex, the requirements for equipment grounding are likely to evolve. One trend is the increasing use of electronic equipment, which can be more sensitive to voltage fluctuations and electrical noise. This may lead to stricter requirements for grounding and bonding to ensure the proper operation of electronic equipment. Another trend is the increasing use of renewable energy sources, such as solar panels and wind turbines. These systems require special grounding considerations to ensure safety and prevent damage from lightning strikes or other electrical events. As electrical systems become more integrated with the Internet of Things, yet there may be new challenges for equipment grounding. Ensuring the security and reliability of IoT devices will require careful attention to grounding and bonding. The NEC is constantly being updated to reflect the latest advances in technology and electrical safety. It's important to stay informed about the latest changes to the NEC and to ensure that your electrical systems comply with the current requirements. Education and training are also essential for ensuring electrical safety. Electrical workers need to be properly trained in the principles of equipment grounding and the proper installation and maintenance of EGC. Continuing education is important for staying up to date with the latest changes in the NEC and the best practices for electrical safety. Public awareness campaigns can also help to promote electrical safety and prevent accidents. Educating the public about the importance of equipment grounding and the hazards of electric shock can save lives. By staying informed, getting trained, and promoting public awareness, we can all contribute to a safer electrical environment. Remember, electrical safety is a shared responsibility, and proper equipment grounding is a critical component of ensuring electrical safety for everyone.